I appreciate the opportunity to be here today, or this evening, or I guess it's early evening for you guys. Let me close myself out. I don't want to stare at myself. Apparently Zoom is giving a lot of young people body issues, like they don't like to look at themselves while they're talking to other people, but I've had body issues. I've never had body issues, so I don't know what that means. But I came on today because I wanted to talk to you guys about some stuff that we've been doing for years, but continues to evolve in seismic geomorphology. It's really analysis of paleo landscapes and seascapes and what I've come to call accommodation-scapes. And we'll talk a little bit about what those are and how we apply that in exploration and development, and also how we're beginning to think about the application of this type of geomorphologic land or paleo land analysis to address risks and hazards and engineer things around the world. So I'll talk first a little bit about landscapes and seascapes and accommodation-scapes. And then I want to talk a little bit about going from pretty images to process, because process is really important to get at accommodation-scapes. And then the second half of the talk is really an outgrowth of some of my younger students and younger people talking about and trying to feel out where geoscience is going. I want to talk to you about the future of landscape, the landscape of geoscience, and then how to use our knowledge of the past to navigate the future. So we have always been fascinated with landscapes and seascapes. They and their formation. They form the foundation upon which all sediment is accumulating and where all tectonics are modifying the Earth and other planets. Yes, landscapes and seascapes and accommodation-scapes exist on other planets, as we're discovering really heavily this week with the exploration of Mars. We've always been fascinated with these landscapes and seascapes. This is a shot from around 1900 of the same Grand Canyon that we're fascinated with today. For thousands of years, we've looked at landscapes and how and what our place is in the earth and in time by looking at the landscapes around us. The very first, what we think is the first map, was created between 700 and 500 BC. It was an interesting little map. It's a clay tablet, and it's about the size of an iPhone, and it's a map of Babylonia. It has the Euphrates River right down the middle of it. It has the city of Babylonia located at the intersection or divergence of the Euphrates River. And it has an area out here that's labeled on it. It's called Bitter Water, and they believe that that's the ocean, or what they thought was surrounding Babylonia. And down here at the mouth of the Euphrates, calls it a swamp, and there are these several sort of triangular features on the outer rim of the ocean. And so this map was really meant, to give the user, not necessarily for navigation, but give the user a sense of perspective of where the holder sat in the world. And so this has been going on for thousands of years, us trying to understand landscapes and looking and gazing at landscapes and mapping landscapes to try to understand the context within which we exist. With the advent of 3D seismic, this has only broadened, right? So now we became to where we got to where we could look not only at modern landscapes, but we could look at ancient landscapes. This happens to be, I really think this is probably one of the best seismic geomorphology papers I've ever seen. And it's by Frode Hadler Jacobsen, a good friend of mine that works for Statoil, now Equinor, and his colleagues. And they published this as part of the GCS SEPM session that we did on seismic geomorphology back in the mid-2000s. And it's a mid-Campanian sort of paralic to deep water basin in offshore Brazil. It's the Cretaceous And so you can really see and begin to visualize what the topography looks like all the way from the subaerial coastal plain off to the beach ridge systems and the offshore systems and shelf environments. And then finally into this, what I call a cross shelf incised canyon that's feeding directly down into a submarine fan system. And so these type of topographies really broadened our sense of what landscapes and seascapes looked like. But it became obvious that not all seascapes and landscapes are composed of a nice, simple bathymetric or topographic profile. Both the Grand Canyon subaerially in this area, which happens to be in offshore Morocco, offshore eastern Morocco in the Safi Hot Mer area. We published on this several years ago, and Dallas Dunlap did a lot of publication with me on this area. And this is quite a complex topography. And so as we began to look at these topographies, we began to realize that the ability to sort of fill space was not only associated with accommodation, which we tend to think of accommodation as the space that's available for sediment to fill, but it was also began to become a much more complex process. There are two variables that allow sediment to collect in a space. There's the topography, and then there's the flow characteristics and how those flow characteristics interact with the topography. We may have a very simple topography where we have this beautiful gravity flow, and it's this sort of a classic gravity flow, right? And it has that beautiful spiraling upward sort of, roll to it, and it's moving down that very simple topography from proximal to distal. But if we complicate this with a little bit of topography, we can begin to see where we run into trouble by just looking at the accommodation space. Here we have a flow that's moving down the system, but I'll just take it back, and you can see that it originates as a single flow. But when it hits the very first accommodation pod, it begins to break into two different flows. The flow on the upper right is moving much faster than the flow cloud on the left, and it continues to head off down slope. And now it's moving so fast, it's even curling around and expanding laterally into topography. In front of it, it's getting hammered by the later flow that's coming down through there, and it begins to progress its way on down through the slope system to fill and interact with this topography. So here's the other thing that happens with this. You can see right to the right side of this image that flow is running into that topography, and it's simply super elevating above the bed. That small triangle in front of that knoll is not getting any sedimentation. It's not getting any, maybe some erosion, but it's not getting any sedimentation. And we see this in complex topographies. We see this in gravity flows in the Gulf of Mexico, and we see this. I can remember, Johnny Hull, I think, a guy that I used to know, and he showed me a talk one time on Chingete in West Africa. And at the time, he was thinking that this was what was happening, that there were some void, these sort of circular void areas around the front of Chingete that you weren't getting any topography, or you weren't getting any sediments deposited. And so what we've come to realize over the years is that, what ends up happening in these systems is it's not just, you can't just put a cap on that feature right there and say, here's the accommodation that I'm going to fill up, right? It also is how the flow characteristics are sort of interacting with that accommodation and how they're behaving in and around that accommodation that results in the types of fills that we see in both the deep water systems and even in fluvial systems, and as I'll show you, even in aeolian systems. And so what we've come to appreciate is that we no longer think of these systems, or we think of these systems as, as seascapes and landscapes, but we also want to talk about accommodation-scapes. And the accommodation piece of this, accommodation is just making room for something to happen. That's all accommodation is. And scape is a suffix that denotes a specific scene, like a seascape or landscape or a moonscape. And in this case, an accommodation scape. A scape or a scene where we're looking at how sediments are being accommodated and the characteristics of that scene, both sedimentologically and both topographically that allow sediments to collect in a space. So what I'm saying to you is you can't divorce the shape of the container from the type of flows that are entering the system and how they interact with that shape of it, with the complex shape of that container. And then you've got to layer on top of this, whether you're dealing with, meandering or fine-grained fluvial systems, whether you're dealing with, coarse-grained braided fluvial systems, what types of aeolian systems are you dealing with in terms of how topography is influencing aeolian dunes and things. Are you dealing with high density or low density gravity flows, et cetera? So this becomes quite a complex thing to have to deal with, and geologists and process sedimentologists and people need to sort that out. So if we go into this, realm of seismic geomorphology, we can look at an image like this, and this happens to be from the Neogene in the West Natuna Basin in Indonesia. And this was one of the first data sets that I kind of fell in love with. I remember seeing this, I want to say it was 97, I can't remember. AAPG was in Denver, and there was a guy named Keith, I can't remember Keith's last name, but he had this amazing image of 3D seismic data that filled an entire 8x4 poster area. And I remember going to him and saying, hey, I'd really like to have that data. And he was he's a really great guy. I've seen him, he's a great guy. And so he said, oh, okay, well, sure, I'll see if I can send you that. And I got back where I was working at the Bureau of Economic Geology, and about a week later, this data shows up. And I was like, he just sent this data. So he just sent this 3D data volume of the West Natuna Basin. And I ended up actually putting a contract together for this data, to cover myself for it. But this was the first real data set where I could see and visualize that there were different types of systems that were existing within these data sets. You could image these high sinuosity versus lower sinuosity versus almost, net cutoff and chute cutoff systems. There were some very straight fluvial systems, and I began to work on these ideas that it's not only the accommodation space that's being created, but it is the way the depositional systems are interacting with this accommodation space to create this accommodation scape within which we're filling these basins. So Henry Posamentier sort of coined some ideas about seismic geomorphology, and I hate to call him the grandfather of seismic geomorphology because he's not that old and he's still running marathons. But he's hanging out now in Bodega Bay, so if you ever want to see him, you can stop in and see him there. But Henry and I shared a lot in common, but one of the things that we shared in common was we were both geomorphologists. And so about the same time, I began working on seismic geomorphology, and I began looking at not just the landforms and the things that were being imaged in the data, but I was interested in quantifying the landforms because I knew that the form in some ways, denotes the process, and so quantitative seismic geomorphology is based on a premise that form denotes process, and that the process, it directs the sediment types and the spatial distribution and the architecture of the system. So I can go in and look at the architecture of the fluvial system and whether I have chute cutoffs or net cutoffs, and I can say something about whether it's a coarse-grained or fine-grained system. This is the same geomorphic concepts and ideas that allow us to look at the images of Mars and interpret, just based upon form, the processes that are going on Mars. Now, of course, we have these beautiful images that are coming back showing these amazing cliniforms, top sets, foresets, and toe sets of these sort of lacustrine cliniforms and things. But before and right now in the exploration of other planets, all we have are images, right? And so this idea that geomorphologically we can measure channel width versus depth, we can look at the radius of curvatures. We can look at the sinuosity of a channel system. We can look at the length versus width of lobes and the shape of Barchan versus transverse dunes and things. And we can say something about the nature of those. Excuse me. So this is sort of shape-based analysis, and we've been doing this for a while, right? And so, excuse me, I need a mute button, right? And Zane Job, a colleague of mine at Colorado School of Mines, Zane's amazing. He and I both, he's drunk the Kool-Aid as well, and he feels very strongly that, about this idea about collecting quantitative data on different things. And we believe that in collecting quantitative data on morphologies and different types of systems, we can create some principles or understanding of algorithms where we can predict what the nature of those deposits are. And we can better understand the relationship between topography and morphology. And so this is truly shape-based analysis. Now, this whole concept of quantitative geomorphology, took a step forward whenever someone had the good graces to produce PaleoScan. And I have to admit, I was very skeptical when PaleoScan came out. This is an image from Steve Tobias's HGS talk in 2018. And Steve gave a talk on the state of the art of using such tools as PaleoScan for digital mapping of landscapes. And like I said, I was very skeptical back in 2010, 2012, when PaleoScan began to come out and people began to use it. We had been doing the same thing, mapping in amazing detail and slicing through data, in 10 millisecond slices. But PaleoScan, I was pleasantly surprised that PaleoScan seemed to be the real deal, and it does seem to do a really good job under guidance of digital mapping. Now, that's what's important here, is that digital mapping anything digital can go very, very wrong if it doesn't have sort of what I call the hand of God or guidance, of the process, right? A word of caution, would be that computers and engineers actually need geoscientists, because if you defocus to the point to where you don't put some truth into what you're doing, you can very rapidly go off an off-ramp that you really don't want to be going off of. And so these guys working together, with engineers and geophysicists, has always been a better tool than just working in solo. We actually need geoscientists to place a grain of truth. And I'll show you, this is an example of just sort of computer mapping a digital landscape, and I call this digital landscape mapping failures. This is actually from one of my students' dissertations, and this was a first pass at sort of mapping the lower Tuscaloosa. It was a total isopack of lower Tuscaloosa, and it does the basics. It shows, the thins are purple in here, right? And the thicks are green, right? And so it's showing the basics. But I think, but what we need to do with this is we need to apply the knowledge of modern system morphology, and applying that knowledge is indispensable when it comes to truly mapping and understanding these geometries and architectures. So if we're to truly understand the accommodation-scape of the lower Tuscaloosa, we need to, what I say is, apply the hand of God. And I don't claim to be the God, but, I could take a map like this, and I could bust it with a little bit of knowledge to really make something meaningful. So, this is the paleogeomorphology of the P0 Tuscaloosa time. So this is breaking it apart. And you can see that we have fins for a reason. They're highs, probably older structural highs. This is from Ewing's, some of older mapping of Ewing stuff, and they're not in exactly the right location, but that's okay. These show general fins, and then the thicks can be made sense of. And we began to look at different source systems. We began to look at different thicks, and moderately thicks, and then sort of thinner areas within these. If you place some context, if you place the computer mapped information within some context. Now, the problem is this takes a lot of time, and it's laborious, and we don't have good regional 3D across here to do this. But in areas where we do have good regional 3D, we've been able to advance our understanding of architecture in the basin by collecting sort of quantitative information on the 3D seismic that we use across the basin. So this is the same West Natuna Basin data that I was showing that Keith gave to me. And this happens to be the upper 200 milliseconds, and it's coming from bottom to top, and it's slicing through every 10 milliseconds or so. It's slicing through this data. Now, every 10 milliseconds here is probably about 10,000 years of time. Okay, and you can see there are systems that are running northwest southeast. There are systems that are running northeast southwest in here. There are these really high amplitude, sort of moderately sinuous features that are busting through. There are these really low sinuous features that are busting through. So there's a really huge complexity. And when I show this, the green are well penetrations. But when I show this data from the Balantic and the Gabas areas, engineers pale, right? Because there's so much complexity in here that they just want to upscale everything. But you can at least upscale things with some knowledge of the architecture of the systems and what you're doing. So if we go through here and look at the architecture of this, let me give you a context here, okay? So if you want a context for what the size of this data set is, I've taken the data set and I've sort of superimposed it over Houston to Galveston. This is sort of the long length of the data. It's about 50 miles by maybe 40 miles or so, but this is a huge area, all right? And so if you want to produce this area, we need to begin collecting some information on this. So we went through and we took every one of those 10 millisecond slices or so, and I've sort of summarized them together here. But we took each one of those slices, and for instance, this is sinuosity. And we just went through and documented the average sinuosity of 10 common fluvial channel systems, or I shouldn't say 10 common ones, randomly selected, gridded across the area. We're just going to take 10 or 20 of them, and we're going to take those, and those 20, we're going to average the sinuosity. And if you look across the study area, you can see this is a running average of sinuosity across here. And you have these cycles of sinuosity, high sinuosity and low sinuosity, going back to high sinuosity periods in the basin, the low sinuosity, and then finally getting a little bit more sinuous towards the very, very young section up here. And if you look at some of these cycles of sinuosity, they seem to have a relationship to the tectonics of the basin. So, there's a phase of sort of rifting in the basin, and then the immediate post-rifting shows some high sinuosity. And then as we go into inversion, early in the inversion process, we have low sinuosity, but then during syninversion, we begin to get a series of high sinuosity channel systems. And then when we get into post-inversion, we get another long period of high sinuosity channel systems. Now, the other thing that we see in this basin, and this is really important, so these changes in sinuosity are really important if you're trying to produce out of this area. And that's what they're trying to do. They're trying to produce gas deposits out of this area. And so if you come into this basin, the other thing that you need to be aware of is whether you're in post-rift or syninversion or post-inversion time in this basin, the fluvial channel systems are shifting orientation. In the post-rift time, we see a northwest to southeast orientation in the Balantic Gabas area. In the post-inversion time, called the Muda Formation, we see a northeast-southwest trend. And this has to do with having gone through inversion and pulling apart, and then a syninversion in the Orang Formation where you get these pop-up structures unfolding and you get a reorientation of the fluvial systems. So you don't want to be putting wells down and injecting and trying to produce with a post-rift sinuosity, geometry, and orientation. Whenever you're in the Muda, you want to be aware that not only does morphology change, but orientation of these systems change. With that in mind, we can go in and look at things like average channel width, whether we're post-rift, syninversion, or post-inversion. And these are significantly different P50s for the width, of all of these channel systems. So this has an effect on net to gross. It has an effect on targeting and how you want to produce these. The other thing that we notice, if we zoom in even tighter on a single channel system, when we sort of pull that out and look at the morphology of that channel system, we can see that we have scours, scours, scours at very specific points within this channel system. Really, right after you make a turn in the morphology or the bend of the channel system, you get a narrowing of the channel and a scour. So there's a bend in the system, you get a narrowing and a scour. Here's a bend in the system, and that's where you narrow and scour the system. And finally, here's a bend in the system, and that's where you narrow and scour the system. Here's another one. So now we can look at the plan form geometry of these systems, and we can begin to say something about the three-dimensional character. And this makes sense. If you're narrowing the channel and you're putting these scours on the outer bend of these systems, then that makes geomorphologic sense. So we can begin to use geomorphology to do this type of reservoir characterization approach to a highly complex fluvial system, but a highly productive fluvial system. If we step these concepts up, we can also take these into more of a drainage basin or a watershed scale. This is from a paper. I've got the reference to the paper by a really super bright young man named He Chen. And He is now an assistant professor at the University of Petroleum Beijing. And he took a postdoc at the University of Arkansas, and he worked also with us when we were at Colorado School of Mines. And this is Rob Galthorpe. And Rob Galthorpe has a deep history in rift basins. He spent his career working rift basins. And this data that you're looking at is from Woodside Energy. And Woodside had this amazing data set, and they were really great partners to loan us this data to be able to work this problem, which was we were trying to answer questions about, the Kendry Trough had always been played up along the margins of the footwall of the Rankin Fault. And from the platform to the Kendry Trough, we were trying to predict the distribution of coarse-grained sediments. So He went in and did this amazing mapping of not only off in the trough. If we look at this cross section, it cuts about right across here. And you can see that here's the Rankin uplift, and that block that's been tilted back to the west or northwest, and all this Triassic strata and the Jurassic strata have been eroded off the top of it and have moved across into the footwall of the Rankin Fault system. And so we were really interested in this interval in here where there seemed to be a dominance of fans between the K10.2 and the Jurassic or the J53 horizon. And there are these dominance of fans down through here. And the question became, if we look at fans all along the foot of that fault, how do we know which ones are sandy and which ones are coarse grain and which ones are fine grain? And what is the highest probability to find coarser sediments off in here? So what He did was he did this amazing map where he mapped the drainage divides along the Rankin platform. And those watershed boundaries or those drainage divides allowed us to track the catchment length. And we could map these catchments for each one of these zones, and there's 6 of them. And then we could do some work looking at and calculating the amount of sediment that's moving out of that catchment, and began to look at sort of sediment budgets along this area. And one of the things that we found were in these variety of fan systems across here, from the Dixon to the Perseus to the Lady Nora, and then the North Rankin, the Eagle Hawk, and the Lambert, that there were trends associated with the Lady Nora, the Perseus, and the Dixon, where the catchment area was not containing nearly as much sediment as the same catchments for the same area of the North Rankin, the Eagle Hawk, and the Lambert. And so we could see that's what these green pods versus these red pods are. This line down in here is from a paper by Somme et al. In 2009. And a lot of people love to use this trend to understand the fan, predict sort of fan areas. But what we find is that when we get into these tectonically active rifted basins, that we need to collect our own data and do our own thing, because the trends don't always match sort of these more mixed trends that SOM. This is an amazing paper with these more mixed trends that SOM has. So we could see that Dixon, Perseus, and Lady Nora were what we call, sediment constrained or sediment limited for their catchment size. And North Rankin, Eaglehoff, and Lambert were overstuffed with sediment for their catchment size. So why was this happening? Well, we could identify along the front of the footwall, we could identify these fans, but we could also identify these channels, these sort of deep marine turbidite channels that were doing what we call toe trimming these fan systems. So they were toe trimming the Dixon, Perseus, and Lady Nora, and they were redistributing the sediment into probably the North Rankin, the Eaglehoff, and the Lambert area. And we had some modern analogs for this. This goes on in rift basins today. Here's the Gulf of Corinth from McNeil in 2005. And Rob Gawthorpe has been working in the Gulf of Corinth quite a bit with IODP. And you can see a similar channel. There's that turbidite channel down through there. And it's what Heck called toe trimming these fan systems and redistributing the sediment into these fan systems farther down in the basin. And so that's what's happening to sediment budgets in here, but you can only see that if you can map the drainage basins, calculate the potential sediment budgets, and then map the fan systems and the morphology of the fan systems along with these turbidite channels. And that paper was published in 2021. It's a Basin research paper. If you guys want to email me, I'm happy to send you a copy of it. If we move to just a screenshot, just a shot of some deeper water deposits, even deeper than the fans. This is in offshore Morocco, and this was some data that that Gabriel and Katrina Cottrell gave us from Vanco Energy, and ONHYM was a collaborator in this, and we share our great collaboration with them still today. And this was a look at an amazing field of deep water sediment waves. And these deep water sediment waves were architecturally moving in and around these salt structures. I don't know if you guys can see my pointer. Let me see if I can do this. There's a pointer there. These were moving in and around these salt structures. You can see the salt structures in there. And you can see this is work that was mapped by Dallas Dunlap. And he could map. He's a great mapper. I mean, Dallas is amazing at mapping and visualization. He works at the Bureau still. And he had mapped these purely just right across the top of these salt structures. So what it tells you, and this is one thing Tobias was getting at in his HTS paper, was using the geomorphology to say something about the timing of structures and the timing of structural movement. And you can see, because of the continuation of a lot of these sediment waves, it was apparent that there was not a piercement of salt structures separating out these different basins. Now, there may have been an influence of the underlying salt topography on some of these, and I'll show you an example of that in an aeolian system here in a minute. But it was clearly not separating these basins out. It was not confining and separating this from the oceanic processes that were going on out here in the front of the basin. We can map these sediment wave fields. The Albion sediment waves are really oriented southwest to northeast. The post-Albion sediment waves are oriented slightly more westward than the older Albion field. So you can go in and you can begin to map sediment redistribution pathways and trends within these systems. You can begin to look at contorites and drifts. I hate the term contorite, but that's a different talk. And drifts, and they clearly extend across the entire area. I mentioned that, you can have these sort of underlying structures that influence sediment waves, both in marine systems that are moving sediments through water movement or through current movement, but also I have a PhD, Don Beelan, and he he's been doing some really good work looking at dune structures, both deep oceanic dunes and also aeolian dunes. And one of the things that we've noticed in the aeolian dune architecture, this happens to be white sands, where there's actually a topographic high running through white sands. And so you have these dunes evolving up over that topographic high, going back down, and then of course climbing off to the west of the mountains. And what he's been able to see is that you have a series of Barchan dunes that transition into amalgamate or transverse Barchanoid dunes. And then near the crest of that high, you have amalgamated Barchanoid dunes. Then as you come back down on the other side, you go back into transverse Barchanoid dunes and then finally Barchan dunes. And then you begin to get vegetation up in the mountains that stabilize these. What this suggests in plan view is that we have a sequence of dunes that evolve as you reach the crest of a structure, and then they devolve down the other side. So it's very systematic in the way they evolve. We think that we could use some of these ideas to begin to look at systems like the Norphlet, and that were clearly deposited over the Luan Salt. And, you know, if we can begin to see areas where there were highs or small pillows and things in the Luan Salt that may have influenced the architecture of the Norphlet dune systems or the Norphlet aeolian system as it was evolving in the Gulf. This is important because Barchan dunes in the lower left have a very different geometry and connectivity than transverse Barchanoid dunes and even amalgamated Barchanoid dunes, and especially parabolic dunes that have vegetation in between them. So being able to build a model to understand the morphology and how the morphology changes as the aeolian dunes evolve over small pillows of salt or tectonic features or topographic highs or ridges, this would be a very useful thing to understand the accommodation-scape over which the Norphlet is evolving. And just as a shout out to my friend Rick Sard, seismic geomorphology and landscape, sea-scapes, accommodation-scapes are not limited to only clastic systems. This is an image from a seismic data, piece of seismic data given to me, by Dallas Dunlap ages ago. It's probably been a decade old now, but you can see that some of the work that Dallas has done, that there are very much morphologies or architectures in this mixed carbonate clastic system with these patch reefs that evolve and represent different stages of progradation within this mixed clastic carbonate system. We see channels that are feeding the shelf. We have a shelf break that's very obvious, or a shelf edge margin. And look at these beautiful tide-dominated little deltas in here, or tide-dominated inlets in between a bunch of these patch reefs. So we see the same thing in this data. We have a bunch of data, which is really great, in offshore Australia. The Australians are very good about just releasing their 3D seismic data sets. And so we can see these same morphologies and architectures evolving along the margin of Australia. So the last system that I want to go through in this part of the talk is, let me see what time we are. Oh, I shut that off. The last system I want to go through, and this is, you know that mass failures are very near and dear to my heart, but we've come to realize and appreciate the importance of deep water mass failures and lacustrine mass failures, both carbonate and clastic marine mass failures. And so we're still doing a lot of research on those systems, and seismic geomorphology has been a boon in understanding the nature of these systems. So if I take you down to Trinidad and the southeastern margin of the Caribbean plate is coming out at you. Here's the Barbados accretionary prism. The volcano that recently erupted is within the belt of the Barbados accretionary, or the Barbados accretionary prism. If we zoom in to that area in plan form now, you can kind of see what I'm talking about with, my pointer's kind of doing its own thing. You can see the area that I'm going to show you next. This is an area where you're getting a lot of tectonic activity and you're getting a lot of mass failures plowing off into this basin. So if we go and zoom in on that area, you can see the proximal shelf margin up in here with extensional faults. You can see these gray blobs are mud volcanoes, and there are a series of entrants into the margin here. This is just a structure map that was built. I think Lorena Moscadelli may have built this structure map. And it's the whole area is about 10,000 square kilometers of 3D, and we slice and dice it down to about 10 seconds or more, right? So if we look at the architecture of these, let me show you what that looks like. So I'm going to stop sharing this. This is probably way beyond my ability to do, but we'll see. So here we are. If we take the seafloor off of this area, you can really see this whole chaotic region of this big mass failure that's coming in and around these mud volcanoes. And if we slice through there, you can see the three-dimensional nature of both transfer faults and extensional or compressional faults and shreds that are coming through there. Let me put this up. You can really see the imbricate thrusts that are being developed as the mass failure moves from proximal to distal, so from close to you to apart. You can also see this levied channel system that's sitting over the top of this mass failure that's in there. So there's a lot of architecture that's being revealed by slicing through the geometry of this, where you can see the dark black areas, which are the mud volcanoes, the chaotic architecture of the mass failure. And as it intersects the lateral margin over here, you have to make a decision. Is that margin going to seal or is it not going to seal? Is the mass failure material to your left of that line going to act as a seal for the material over to the right of that line? And so I find companies running into this question. I'll just take that off. I find companies asking this question continually in deep water. And so this is where we've got to go in and do more work to understand what's the sealing character of these types of deposits, and can we look at and map the structure and combine that with an understanding of either the muddy or the sandy nature of the material, and say something about the ability of these type of geometries to form sealing traps, both in the Gulf of Mexico, and if we're looking at them in Trinidad, we're looking at them in offshore areas all around the world, right? So I'll just put on this, which, and now if we've kind of sliced through, this image is slicing through the levied channel system that sits on top of it, and you can begin to see how the levied channel system is occupying the space over the top of the mass failure. So you have this really beautiful levied channel system. You see this all the time. You see these mass failures that leave unfilled accommodation space in here, and the sediments are coming in and filling this accommodation scape. So if I switch back to the slides, now we're getting to a point. Well, maybe. There we are. The last thing I want to say about the seismic piece of this is something I call the MEG, okay? One of the things that sort of has changed the face of seismic geomorphology a little bit is the birth of the MAG survey, the mega survey. I don't know how many of you saw this movie I've just got to recommend this. This is an awesome movie. It says chomp on this. But I use it to represent the MEG survey because the MEG sort of changes the face of our understanding of seismic geomorphology. It has created an ability to go in and create a step change in our ability to document ancient landscapes and seascapes that characterize the Earth's surface. If we look at some of these mega surveys, a bunch have been collected together in the North Sea. The PGS North Sea mega survey shown on the left is 17 3D surveys covering 138,000 square kilometers. And then look at the massive 2D that's come together. The PGS Barents Sea mega project is 34 3D seismic surveys covering almost 23,000 square kilometers, along with 173 2D surveys. So the ability to merge these surveys together into mega surveys enables us to map the paleo landscapes like never before. On the left, you can see this is a base Cretaceous map in ArcGIS. Okay, and so it is a base Cretaceous map of the entire, southern part of the North Sea, and it informs us about the geomorphology, evolution of the area like we've never been informed before. The other thing that these surveys have allowed us to do, there's been a collaboration between academia and the archaeologists and industry. And so this has resulted in a sort of a North Sea landscape mapping project called the Lost Lands Initiative. And the Lost Lands Initiative has mapped the Mesolithic and Neolithic landscapes of an area called Doggerland. And you can see Doggerland down here. And so they've taken sort of the upper, 500 milliseconds or less of the data, and the companies over in Europe have, this company has allowed them to use these data sets to map the Paleolithic history of these lands. These lands have been termed aqua terra by a professor at the University of Kansas, I think. And so there is a move afoot to collaborate once again with industry to look at the seismic geomorphology of aqua terra. And I'll come back to this before I finish the talk. But this is a non-invasive integration of academia and industry to better understand the evolution of these aquaterran areas around the world. So the last thing I'd like to finish up with, and I'm not sure how much time we have because I turned my phone off. Maybe I should.
You're good. You're good, Leslie.
Okay.
Yeah, you got 5 more minutes or something like that.
5 minutes. Okay, we'll take 10 and say it's done. So what I want to talk to you a little bit about is, this is maybe for the younger crowd in here, but is the landscape, what I call the landscape of geoscience, right? And this landscape that we're talking about has just changed dramatically, right? It now includes critical minerals, geothermal, because kids are always saying, what are we going to work on in the future? Space resources, believe it or not, storm-generated hazards, carbon sequestration, wind farms, offshore wind farms, and the need for water, a whole lot of water. We're not going to talk about the water, but I am going to talk about some of these other issues. We need to take geomorphology and utilize it in some of these other areas of geoscience. And this is where geoscience is going. There is a need for conventional exploration and development, but there's a whole world of opportunities out there to apply our understanding of geomorphology and landscapes and seascapes in these new arenas or these new areas, right? Let me see if I can. I don't know if I can or not. I was going to try to get rid of that. Anyway, for years we've worked on these systems, and believe it or not, this is not an if this is going to happen. This is a when this is going to happen. And we at Colorado School of Mines, we offer a graduate degree in space resources. And this is for mining space resources, both on asteroids, on the moon. We've talked a lot about Mars and the deltas and things on Mars, but where the action is really happening are on asteroids and on the moon. And of course, then there's the methane lakes of Titan, which Dragonfly is going to explore in the next several years. There's a need for critical minerals, and that need is critical. And we need to use some of our experience to map and understand the distribution of these critical minerals. The population of the world is not getting any smaller. We probably have about 7 billion people now. By 2050, we'll have probably about 9 billion or more. And each one of those have always used a lot of petroleum, each one of those people, and a lot of natural gas. But what you don't think about are the copper, the lead, the iron ore, the bauxite and aluminum, the salt. I mean, all of those minerals that people need to survive on the earth. The other thing that's coming around are the growth of mineral needs for low carbon energy technologies. This is actually a picture of lithium. And lithium, one of the things that you'll notice in this graph on the upper left is that aluminum, copper, manganese, these are the things that we currently mine a lot of. And we use a lot of because we have a demand or we have a need for them. But what you don't see in here is the demand or the need that we are going to have by 2050 for graphite, cobalt, and lithium is huge. And currently we mine almost nothing. Okay. And so we need to do a better job of beginning to look at critical minerals and also geothermal environments within the volcanic accommodation-scapes that we can map using our seismic data. This is an area where we need to step forward and sort of train people in how to interpret craters and conduits and sills and volcanic deposits and their interaction with surrounding sedimentary rocks. This is from Chin, once again, the boys out there doing some stuff now. And this is a paper that he's preparing on seismic geomorphology, the accommodation of volcanic landscapes. And these are the type of areas that we'll be searching for in the future to understand geothermal energy and understand critical mineral distributions. One of the other areas that's going to change and that we need to input into are storm-generated hazards. And probably I'll just show you, there's the size of storms are only going to grow as the earth warms. They're impacting deeper and deeper areas of the seafloor. They're destabilizing larger and larger areas. Insurance companies like specialists in catastrophic risk modeling specialists like RMS show that there are going to be huge losses from North Atlantic hurricanes. They could increase as much as 25% by 2050, and the European floods could cause at least a 60% increase in insured losses by 2050. So there's a need for us to understand the past and to be able to use things that have happened in the past to predict what's going to happen in the future. Modern storms, the wind speed of modern storms has normally been up to about, 70 meters, 60 meters a second, right? But when we saw Katrina and Superstorm Sandy and even Ivan come in, their wind speeds are catastrophically higher than what we've seen in the past in modern storms. And so we're already seeing storms increase in their magnitude, if not their frequency. If we look historically at the record in the Western Interior Seaway, we see that there's evidence in hummocky cross stratification there that we've seen fully developed seas and swell waves that are at least as large as modern storm systems. And these are just swell waves. These are just waves that are coming off of associated storms that are probably happening in the proto-Gulf of Mexico during the Cretaceous. So we need to prepare ourselves for a series of really large storms that are coming down the pike. And we need to understand as a group of geoscientists that we have an obligation to understand how people build structures and infrastructure along the margins of the continents, and how we're going to manage that. Some of the things that we see or we're going to see are destabilization and destruction of seafloor infrastructures. We're already seeing an increase in the friction and wear on shallow marine cabling. We're compromising rigs and rig emplacements, and there are seafloor failure generation of tsunamis that are occurring. In September 16th in 2004, Hurricane Ivan hit, and it had 33-meter storm waves. That's 100-foot high storm waves. It caused a landslide off of the Mississippi Delta that slammed into the Taylor Energy rig and threw it 170 meters from its location. So we need to better understand. It actually caused an oil slick that nobody wanted to deal with, and that lasted up until 2018 when someone, this is, 14 years later, somebody finally plugged this oil slick, right? But we need to better understand how these processes are going to impact what's going on along the margins, these failures, and how we can influence how we build infrastructure along these margins. An example of this, of tsunamis generated by these small failures occurred off of the Nice airport, back in the 50s, when there was a fairly small slide that was destabilized off of the Nice airport, and it loaded off and caused a larger submarine landslide. Regardless of the cause, it killed about 23 people, and it swept them away and sent a huge inland tsunami going in 3 to 5 meters high. So this caused millions of dollars in economic damage. So these failures that are happening due to these increases in storms are going to have an influence on tsunamis that are being generated. All the tsunamis are being generated by mass failures and not by earthquakes. Of course, the other area, and this is beginning to wrap up, but the other area for the landscape of geosciences is carbon sequestration, carbon capture and sequestration. Biden's asking Congress for $35 billion to generate solutions to the climate crisis, right? And it's apparent that we should be well prepared to transition our science, or expand our science, I shouldn't say transition it, into questions of carbon sequestration. Some of the key questions: how big is the plume? Will the top seal hold? Will the fault seal? If we inject, how far will this migrate? Will it get onto other leases that we don't own? Will it intersect older wells and corrode casing? Do those sound familiar? Those should sound familiar. Those are the same questions that we've been asking for 100 years as we've worked geoscience to extract resources. Now we need to answer those same questions and turn our talents towards answering some of those questions to sequester carbon back into either deep saline aquifers or some type of subsurface offshore or onshore reservoirs. Finally, the last point I want to make have to do with wind farms. Seismic geomorphology of this area of Aquaterra, which is shown here in red around the world, is a prime area for wind farm development. So understanding the seismic geomorphology of Aquaterra can have a dramatic impact on our ability to establish offshore wind farms. Just 3 days ago, Ørsted AS had commented, an article was published in Rig Zone, published from Bloomberg, talking about nearly $500 million that Ørsted AS is going to have to pay to fix damage that's been caused on the cables offshore in their wind farms by scraping against rocks and currents that are moving the cables around. We know this. We know that there are strong currents moving in the offshore because this is what we do as geomorphologists and as geologists, right? Currently, there's a wind farm proposed in offshore New York, and this is a report from New York State that shows the current lines around the green area is the wind farm proposal. And these are undersea cables that currently exist. One of the things that you don't see on here is you don't see this. This is the tract for Superstorm Sandy that came ashore in this area. And these storms are only going to exacerbate the destruction of these floating wind farms and the corrosion of cables and the undermining of infrastructure that's happening in these areas if we don't understand how the storms are influencing erosion on the seabeds and how we can mitigate and engineer around some of those problems. But in this report, I will say this, you won't find any geoscience in this report. It's all about infrastructure and it's all about engineering in and around all these cable structures. We need to get more active in being involved in this. We could do the same type of study that was done in Europe using the upper 500 milliseconds data in the Gulf of Mexico. Answer questions like, how did the aquitarians respond to global sea level rise? Was it through mitigation or migration? How will our rivers, deltas, and shorelines respond to global sea level rise? What will be the impact on our infrastructure, both aquatic and subaerial along the margins? How do increasing storm intensities impact the substrate in the aquitarian areas of the Gulf of Mexico? We have the tools together as an industry to sort of begin to share data and compile these things together. And I noticed that Carrie Campbell was on this talk. And Carrie Campbell has been a champion for decades. I've worked with Carrie to obtain data from Fuga McClellan and to work in these aquitarian areas to understand the morphology of these systems. And so I have to give a shout out to him as a champion for this type of work. So the present is not the key to the future, but the past might be helpful. If we can utilize the data that exists within our industry and within our coffers to better understand some of these processes that are going on in these landscapes, seascapes, and accommodation-scapes around the world. Paleogeomorphology really is our key to understanding the future of the Earth. It can help initialize risk assessment and exploration and development. It provides the data to build predictive models of form and process and deposits. It shows us how to recognize changes in geomorphic systems and how to predict system response. We can look at the accommodation-scapes to understand the system, but we need to work with the engineers and facilities designers to build things that withstand the processes that are to come. We hold the keys to inform lawmakers, industry, and populations of the way the scapes around them will evolve in response to change. And through this awareness, change behavior and how we deal with that. And finally, industry and academic partnerships are critical to utilizing industry trim. Really, it's the trim from industry data, for a new understanding. So I appreciate your patience, and I will keep sharing, I guess. I'll thank a few people here, so.
Go for it, Leslie.
No, go ahead. I was just going to put this slide up because it just, I started writing out different people who had given us data and supported what we were doing. It was like over 20 years, we've had immense amount of partnerships with an immense amount of companies. And we think that we're actually talking with some companies still now about releasing a huge amount of data. So I have to thank Dr. Lorena Moscadelli. She's been a partner in crime to me for years. And I don't know, most of you probably know, she recently took up a position as the director of State Lands Research, the STAR program at the Bureau of Economic Geology. And I'll thank Dallas Dunlap, a good friend of mine, and of course, Hehe Chen, who's evolved as to take over the mantra of seismic geomorphology in China. So that's it. Thanks, guys, for your attention.
No problem. Well, thank you, Leslie, for the very informative talk. And so with that, I wanted to go ahead and open up the floor for a Q&A session, but I did want to start with a couple of comments. So Andy Pullham wanted to thank you for the great images in the talk. Leslie, he had to jump off a little early, but he sent his thanks. And also Dirk Bodner said the platform in MC20 was his first drilling and production platform. So
is that right?
yeah,
Nice.
he said, Ivan and the
You gotta start somewhere.
Sure hit things, he said. So, but you know, we are running a little bit late on time, and I think I haven't had any questions just submitted yet, but I feel like it'd be very easy to reach out to you directly. Do you have an email that I can share in the chat for anybody who wants to reach out to you?
Let me find, I would type it. There we go. Yeah. So everybody kind of knows how to find me.
Yeah, I think so.
Yeah, do that or give me a call.
Perfect.
Or come and see me. Better yet, just show up.
Awesome. Awesome.
Okay, guys.
Well, I hope you're enjoying the snow up in Evergreen, Leslie.
Yeah.
And
got plenty of it this year. I hope you guys are enjoying I hope you get some heat and humidity soon for you.
Exactly. Well, thank you so much once again. We really want to thank you from the HGS for taking the time to share your thoughts and insights, and we really appreciate it. So we look forward to future talks that you will give for the HGS, and also attending your talks that you will be giving at other conferences and societies. So thank you for all that you've done, Leslie.
Yeah, thanks a lot, man. I appreciate you being involved, okay?
Not at all. Well, with that, I'm going to go ahead and end the session. So to everyone, thank you all for joining, everyone else who joined, and please reach out to Leslie if you have any questions or concerns about her talk. And with that, this is going to end the general HGS dinner for May 2021. So see you guys next one.
All right, guys. We'll talk to you later.
All right. Thank you.
See you, Margaret. Carrie.